Welcome to the class. We have seen that how does a Brayton cycle work and how to do calculations for various performance parameters for Brayton cycle. Then we moved on and considered the efficiencies which are isentropic efficiencies for turbine and compressor. Then now we are moving towards next reality where we are going to consider turbine and compressor efficiencies along with the combustion efficiency, and also we will account some more things which we had not accounted. So the thing which is we are going to account here is the stagnation condition. Now if we go back and see what did we consider and what we did not consider. Now if we draw our Brayton cycle, then in TS diagram we drew our Brayton cycle like this, where 1, 2 dash, 3 and 4 dash was the cycle which is ideal cycle, and when we said that we want to consider real, then we said that okay, 1 to 2 is compressor and 3 to 4 is turbine. So this is what we had considered till time. Now here while working with, we made certain assumptions. First assumption we made was we neglected potential energy between inlet and outlet of compressor or turbine. So potential energy is neglected. We neglected kinetic energy change in potential in turbine and compressor. So delta PE and delta KE we neglected. Then we also considered Cp and Cv and gamma, they are constants. We considered them as constant. Further, we took into account that the losses in combustion are negligible, no loss in combustion. So with these prominent assumptions, we derived few things for the Brayton cycle. But now we have to move ahead and neglect some of the assumptions. Prominently we will neglect the assumption what we made for consideration of KE. Rather, the assumption which was considered as change in kinetic energy is 0 and no loss in the combustion chamber, we will now not consider these as assumptions, and we will counteract for that assumption and take proper action for those assumptions. While considering that, we have to first know what do we mean by stagnation condition. So whenever we talk about few things in case of thermodynamic or fluid dynamic parameters. Suppose I consider P, which is pressure, then we say that there are two types of pressures. One is static pressure or other is stagnation pressure. Dynamic pressure also exists, but here we are talking about P. Dynamic pressure is half rho v square. So this P pressure is either static or stagnation. Similar thing exists for temperature, density, entropy, enthalpy and all other properties. So all other properties are existing with two versions, one is static or other is stagnation. So what is the difference between static properties and stagnation properties? Now we mean here by saying something as static, so let's say pressure as static pressure or temperature as static temperature, then we mean that the quantity is measured in the presence of velocity. So if velocity is not brought to 0 and a quantity is measured, then that quantity whatever we measure is called as static quantity. So if it is a pressure, then it is a static pressure. If it is a temperature, it is a static temperature. So here velocity is not 0. Now if we consider stagnation, which is also called as total, while considering this, velocity has to be brought to 0, but it has to be brought to 0 in isentropic way. So it has to be brought to 0 reversibly and adiabatically, then the corresponding condition is called as stagnation condition. So here, as static condition P is dependent upon x, y, z as location, so pressure is varying in all the locations in the flow field. Similarly, if we denote P naught as the total pressure or stagnation pressure, then that will also vary at all locations. So it is a spatial quantity which has to be evaluated at a point where we have to assume that if at that point the fluid particle is brought to 0 velocity isentropically, then what would be the condition. With this assumption, if we measure the pressure, then corresponding pressure is stagnation pressure or total pressure. So here we are bringing the velocity to 0, as P naught is having 0 as subscript. Similarly, T naught, rho naught, H naught all represent stagnation conditions at a given location. So it is an imaginary quantity which one has to calculate by thinking or by assuming flow to be brought to 0 velocity isentropically. But there are certain realities where we can practically measure this, and then that is where we say it as pitot static tube, where we have, this is a tube in which we have a hole at the center, and this center hole is connected to a limb of manometer. Then fluid will go here, and practically fluid is going to rest at this location. So if we measure pressure at this location, then this pressure is called as, this pressure would be called as total pressure or stagnation pressure. So if I take a cylinder or sphere and flow is flowing over, and then I measure pressure at suppose 3 locations, 1, 2 and 3. At location 1, flow would directly come to rest since it is a stagnation point. So the pressure measured at point 1 is a stagnation pressure, but at point 2 flow will be not stagnant, since the normal direction is this at this, and velocity is not in the direction of local normal. So there is a component of velocity which is not letting it go to 0, and then that is why velocity not being 0 at point 2 and also at point 3, the pressure measured at point 2 and 3 is a static pressure. Similarly, if we measure density or measure temperature at point 1 and point 2 and 3, then those will be static quantities, and the quantities whatever we measure at 1 will be total quantities. So this is the basic difference between stagnation and static quantities. So we are assuming that flow is brought to 0 velocity isentropically. So we have to consider isentropic relations, and as isentropic relations we know that P2 upon P1, we have always used this relation for Rp, which is pressure ratio, and we said that T2 by T1 is equal to P2 by P1 bracket raised to gamma minus 1 upon gamma. The same relation we are saying that P2 by P1 is equal to T2 by T1 bracket raised to gamma upon gamma minus 1. Suppose this is a streamline, this is state 1 and this is state 2, and at state 2 we have brought the fluid to 0 velocity. So P2 is nothing but P naught, and it is P1, that is equal to T naught upon T1 bracket raised to gamma minus 1 upon gamma. Similarly, rho naught upon rho is equal to T naught upon T bracket raised to 1 upon gamma minus 1. Then we will go ahead and try to link it with classical gas dynamic relation, where let us apply the steady flow energy equation between station 1 and 2. Then it says that H1 plus V1 square by 2 is equal to, ideally this equation says that we have to add heat, then H2 plus V2 square by 2 plus W dot, or W, since units are kilojoule per kg. But we are saying that there is no heat addition between station 1 and 2, and then there is no work interaction. So we will have H1 plus V1 square by 2 is equal to H naught, where fluid is brought to 0 at station 2. So we will write H naught is equal to H1 plus V1 square by 2. We can write down H naught as Cp into T naught, where we are considering it is a calorically perfect gas, since Cp is not varying with respect to temperature. So it is Cpt1 plus V1 square by 2. This further can be simplified by saying that Cp after division would lead to T naught is equal to T1 plus V1 square by 2 divided by twice Cp. Let us divide both the sides by T1. So we will have T naught upon T1 is equal to 1 plus V1 square by 2 divided by Cpt1. We know that Cp is equal to gamma R upon gamma minus 1. Hence T naught upon T1 is equal to 1 plus V1 square by 2 gamma R upon gamma minus 1 into T1. So T naught upon T1 is equal to 1 plus, we can take gamma minus 1 at the top, so we will have gamma minus 1 by 2 plus, into V1 square divided by gamma RT. But we know that gamma RT is equal to acoustic speed square. So it is 1 plus gamma minus 1 by 2 V1 square divided by A1 square. But as per the definition of Mach number, it is 1 plus gamma minus 1 by 2 M1 square, since gamma RT 1 is equal to A1 and V1 upon A1 is equal to M1. So knowing these things, we could derive a relation for T naught. So we will write down here and say T naught upon T1 is equal to 1 plus gamma minus 1 by 2 M1 square. So knowing this, we can write down same relation for pressure as total pressure. So P naught upon P1 is equal to, we can remove the subscript 1, so it will become T naught upon T is equal to 1 plus gamma minus 1 by 2 M square. We can as well add subscript as infinity, which means that free stream condition. So anyways, subscript can be as per our requirement. So P naught upon P is equal to T naught upon T bracket raised to gamma upon gamma minus 1, which is equal to 1 plus gamma minus 1 by 2 M square bracket raised to gamma upon gamma minus 1. Similarly, rho naught by rho is equal to T naught by T bracket raised to 1 upon gamma minus 1, which is again 1 plus gamma minus 1 by 2 M square bracket raised to 1 upon gamma minus 1. So if we know a Mach number at this location 1, then knowing the Mach number at location 1, we can put that value over here, and then we can calculate P naught, T naught, rho naught H naught and all the quantities which are required at station 1. So, this is what we call as stagnation condition and the stagnation condition relations. So, here all these relations are based upon the fact that we are assuming flow to be brought to 0 velocity with isentropic assumption. Now, let us go back and see what do we mean by not accounting the velocity we have got. We did not account the velocity and we have got certain relations, but now we will start considering the velocity with the help of stagnation condition and try to find out the same relations for Brayton cycle. So, we know that our Brayton cycle had a compressor which is the first entity, and then for the compressor we have process 1 to 2, and then we have 3 to 4 as turbine. So, for compressor 1 to 2 we will consider the steady flow energy equation. So, we will draw the compressor in the Brayton cycle. So, this is station 1, this is station 2, this is compressor. So, we will apply the steady flow energy equation which states that H1 plus V1 square by 2 plus Q1 is equal to H2 plus V2 square by 2 plus W12 or Q12, but we know that it is not interacted in the compressor. Now, earlier we neglected velocity and we said that H1 is equal to H2 plus W12, but now we will not neglect the velocity and we will say that okay, the flow, if it is brought to 0 at station 1, then we will have H1 plus V1 square by 2 as H01 is equal to H02 plus W12. So, if we start considering total enthalpy at station 1 and total enthalpy at station 2, then the work done or work input whatever we get will actually account the velocities at station 1 and 2. So, we are going towards more realistic estimates. So, W12 is equal to H01 minus H02, which is minus delta H naught. Practically this work is added into the system. So, it will become W12, which is work input to the system, is H02 minus H01. So, this is delta H naught. So, we can see that if we add work into the system, total enthalpy increases. So, for the compressor, total enthalpy increases. So, we can now move and add the thermodynamic process for compressor. So, we will say that okay, so this is T, this is S, which is temperature and entropy, and now we will plot particularly 4 lines where we are saying that this is station 1 as what we wrote here. So, this is the static conditions at 1. Now, at 1 we are knowing or needing H01. So, for that let us bring the flow isentropically to 0 velocity. So, if we bring it isentropically to 0 velocity, then we will reach to the not 1 condition. So, this is not 1. Now, as what we were consider earlier, we were considering compressor work to be input in the process 1 to 2. So, 1 to 2 is compression using static conditions, 1 to naught 1 is actually stagnation process for state 1. But now in the new ways we are saying that naught 1 to naught 2 is the actually work input in the process of compression. So, naught 1 to naught 2 is again compression, but it is from the perspective of stagnation conditions. So, practically we have 2 to naught 2 is stagnation process for state 2. So, practically we are having this as half V1 square upon Cp, and then this is equal to half V2 square upon Cp, since this is delta T and this is also delta T, since y is a temperature axis, it is not energy. So, this is not half V1 square, this is half V1 square upon Cp. So, this is what the thermodynamic process for compressor if we start accounting the stagnation conditions, but the process of our interest was here 2 dash. So, here process of which is ideal process actually from our perspective, and not 1, and then we have real process as 1 to 2, 1 to 2. So, 1 to 2 is compression in static sense, which is real. 1 to 2 is a static sense which is real, and we are saying this is a constant pressure line. So, P1, this is P01, this is P2 and this is P02, but really we are now accounting velocities. So, it will become not so it will become not 1 to not 2 dash. So, it is compression from stagnation perspective, and then that is basically in real case. So, as what our nomenclature says, 1 to 2 is real and 1 to 2 dash is ideal or the isentropic process. So, this is how we would draw a new thermodynamic process for compressor. Now, we will see the isentropic efficiency of compressor. We have said that eta C is isentropic efficiency of compressor. Here we know that it is having isentropic work input divided by actual work input. So, we have eta C, isentropic work input will be H naught 2 dash minus H naught 1. This was actual work input, but ideally we will get H naught 2 minus H naught 1. Now, we will consider calorically perfect gas. So, Cp can be used to represent enthalpy. So, Cp into T naught 2 dash minus Cp into T naught 1 divided by Cp into T naught 2 minus Cp into T naught 1. So, compressor efficiency is T naught 2 dash minus T naught 1 divided by T naught 2 divided by T naught 1. So, as what we know, we can always calculate T naught 2 dash knowing T naught 1 or T2 using isentropic relations, or T naught 2 dash upon T naught 1 is equal to 1 plus gamma minus 1 by 2 Rp T naught 2 dash upon T naught 1 will be Rp for compressor bracket raised to gamma minus 1 upon gamma, and we can always calculate T naught 2 dash knowing the T naught 1. So we need to know what is T naught 2. So we can find out T naught 2 using reshuffling this equation, which says that T naught 1 plus 1 upon C into T naught 2 dash minus T naught 1. So having said this, we would calculate T naught 2. So further let us simplify and take T naught 1 common. So it will be 1 plus 1 upon isentropic efficiency of compressor into T naught 2 dash upon T naught 1 minus 1. But as what we said now, we will write it as T naught 2 is equal to T naught 1 into 1 plus compressor efficiency, and then this is Rp pressure ratio for compressor bracket raised to gamma minus 1 upon gamma. Here we should note that we are using not just Rp, but we are using Rpc, which states that only for compressor, and we will see why it is so in next few minutes when we come back for turbine. We should also note here that we are considering that there is no loss in total pressure if we come from knot 1 to knot 2 or from 2 dash to knot 2 dash. So practically we are considering the P naught 2 is equal to P naught 2 dash. So these are the two assumptions which we are making. Now let us go and see that heat addition in the combustion process or combustor. Now first, how did we represent the combustion process? In case of just TS diagram, we said that it is isobaric combustion, so it is said that 2 to 3 or it is 2 dash to 3 dash or 3 accordingly as per the ideal or real cycle. So we were considering that P2 is equal to P3, which was static pressure, but now we will account it in terms of total pressure, and so we will have suppose 2 here and 3 here and process 2 to 3 like this. So first we will go from 2 to 2 dash isentropically. So this is not 2 to not 2 isentropically, such that we will get stagnation condition, and we will go isentropically from 3 to not 3, where we are accounting this as half u V2 square upon Cp, and this is half V3 square upon Cp. And then if we try to connect them, then we would see that this was P naught 2 and this is P naught 3, where P naught 3 is less than P naught 2, and then this difference in total pressure is loss of total pressure due to combustion, and this is how we will start accounting the total pressure loss. So if we start writing the steady flow energy equation, then we can mention H2 plus V2 square by 2 plus Q23 is equal to H3 plus V3 square by 2 plus W23, but there is no work interaction in the heat exchanger. So we have H3 Q23 is equal to H3 plus V3 square by 2 minus H2 plus V2 square by 2. So it is Q23 is equal to H03 minus H02. Since the term in the bracket is total enthalpy at station 3 and this term in the bracket is total enthalpy at station 2. So this can ultimately be written as HCP into T03 minus T02. So this is how we will account the heat addition in the process of combustion, and this is how we will account the delta P Cc, rather delta P not Cc means total pressure loss in the combustion chamber or in the process of combustion. So having said this, we will move towards our next entity, and that next entity is turbine. So in case of turbine, let us find out the turbine work. For that, we will again consider the TS diagram. In the thermodynamic process, we will consider and then we need to draw 4 lines corresponding to static and stagnation conditions. So this is P3, this is P03, this is P04 and this is P4. So for us 3 to 4 dash was the process of isentropic expansion, but now 4 point is brought to 04 and then we get the total condition at 4 point and 3 point is brought to 03 to get the total conditions. So we will have a process like this where we will have this as 04 point and this would be the ideal 04 point, which is 04 dash. So this line represents half V3 square upon Cp and then this difference represents half V4 square upon Cp. So this is how we can get the total conditions at different stations, and then this is the representation for the case where we have this internal is for static, this external is for total. So let us say 03 to 04 dash is expansion, isentropic expansion, ideal isentropic expansion in terms of stagnation quantities. Then we have 03 to 04, so this is expansion which is real in terms of stagnation quantities. And then we have 03, just 3 to 4 dash is ideal isentropic expansion in terms of static quantities, and we have 3 to 4 as expansion which is real, that is with static quantities. So this is what we had also seen in case of compressor. So these are the different processes what we had considered for compressor. So 01 to 02 dash is ideal, 1 to 2 dash is compression which is with static and ideal, 01 to 02 dash was compression with stagnation, and that is ideal. Similarly, 1 to 2 was compression which was with static and real, and 1 to not 2 dash was compression with stagnation condition was ideal. So, the same thing we are looking with the turbine, and then we have plotted the process for turbine. Now, we can use the steady flow energy equation for turbine. So, let us plot. This is the turbine. So, we have station 3 here, we have station 4 here. H3 plus V3 square by 2 plus Q34 is equal to H3 plus V3 square by plus H4 plus V4 square by 2 plus W34. But turbine does not have any heat interaction, so it is H3 plus V3 square by 2 is equal to H4 plus V4 square by 2 plus W34. So, W34 is equal to H3 plus V3 square by 2 minus H4 plus V4 square by 2. So, the terms in the bracket necessarily represent total conditions. So, we have H03 minus H04, and which necessarily represents in terms of temperature as T03 minus T04. So, we can get W34 as delta H0, and which is equal to Cp into delta T0 in the process 3-4 but the major thing in case of turbine, total temperature decreases and total enthalpy also decreases, since we are actually having work output from the system. So, let us consider the isentropic efficiency of turbine, and there we have isentropic efficiency of turbine is equal to actual work output divided by ideal work output. Now, we are trying to represent this in terms of total conditions. So, we have actually H03 minus H04 as the work done, which ideally would have been H03 minus H04 dash. So, in terms of Cp, it is Cp into T03 minus Cp into T04 divided by Cp into T03 minus Cp into T04 dash. So, we have T03 minus T04 divided by T03 minus T04 dash. Here, as expected, the known quantity will be T03. So, from this known quantity we can calculate T04 dash using the relation which says that Rp T bracket raised to gamma minus 1 upon gamma. So, our aim here is to find out T04, and T04 is equal to T03 minus efficiency of turbine into T03 minus T04 dash. So, let us take T03 common. So, we have T04 is equal to T03 into 1 minus turbine efficiency into 1 minus T04 dash upon T03. As what represented earlier, we can replace T04 dash upon T03 ratio using the relations which are isentropic relation, which says that 1 minus 1 upon Rp T bracket raised to gamma minus 1 upon gamma. Here it should be noted that we have used not Rp but Rp into T. So the point to be noted here that we are using turbine pressure ratio. So there are two pressure ratios, one is RPC which is compressor pressure ratio, and then RPT which is turbine pressure ratio, and for the cycle we will generally be using RPC. But why these total pressures are different? Since at the end of the compression we have reached certain total pressure from knot 1 to knot 2 dash or knot 2, but in the process of combustion this pressure got lost, so knot 3. So there is loss in total pressure, and then at the end of expansion we have come back to the same total pressure ratio maybe. But then the total pressure ratio between the inlets and outlets of the compressor and turbine are not then same due to loss in total pressure in the combustion chamber, delta P naught Cc. So there are two total pressure ratios, and within that compressor pressure ratio is always greater than the turbine pressure ratio. Having said this, now we will draw the actual diagram, which is the TS diagram for the cycle. How would the actual cycle would look like? So let us plot the actual TS diagram. We know that we are here at state knot 1. If we are centripetally compressed, then we will go to state which is knot 2 dash. But in reality we would go to a state which is knot 2. If there is a heat exchanger, then there is certain loss in total pressure in heat exchanger, and then we know that our earlier TS diagram with heat exchanger was like this, which was 1 to 2, 2 to 3, 3 to 4. So 2 to 5 was heat exchanger heat addition at the end of the compressor or before the combustion chamber, and 4 to 6 was the loss of heat in the heat exchanger from the gas side. So now if we see the process 2 to 5, it's isobaric heat addition, but due to the flow there is loss in total pressure, so we will have lower total pressure, and then that is knot 5, and then there is heat addition into the combustion chamber, and then we will end up in the point which is here, and we will say it as knot 3. From knot 3 we would come to knot 4 dash, but in reality we will come to knot 4 due to loss in the turbine, but then we will have a heat exchanger in the process, and then that heat exchanger would bring us to knot 6 due to further loss. So this is the real cycle what we can imagine for the gas turbine. Here this is the loss which is delta P naught into the heat exchanger from air side. Similar complementary loss is delta P naught into the heat exchanger for the gas side. So this is the total pressure loss in the combustion chamber. So these are all the losses which we have accounted when we started considering the total conditions, where we have accounted the losses and also we have accounted the velocities. So now we will consider some more facts, and those facts include that suppose m dot A is mass flow rate of air m dot f is mass flow rate of fuel, m dot g is after combustion, which is mass flow rate of gas, which is after combustion. So, m dot g is practically is equal to m dot a plus m dot f. So, if I write really, then we can have to do like this. So, we have state 1 or state not 1, then we have state 2 or state not 2, then we have combustion chamber, and in the after the combustion chamber we have state 3 or not 3, and then we have turbine, and in the turbine we have at the end we have 4 or not 4. In the compressor we have air which is going. After the entry of the outlet of the compressor we have air coming. In the combustion chamber we are m dot f adding, which is fuel flow rate. So, to the turbine we are passing m dot g, and from the turbine we have m dot g coming out. So, if we write for the compressor, then WC, which is in watt, will be m dot a into h naught 2 minus h naught 1, which is m dot a into Cp of air into T naught 2 minus T naught 1. But for combustion, which is Q in is equal to m dot g into T naught 2 into h naught 3 minus h naught 2, which is m dot g into Cpg into T naught 3 minus T naught 2, which is practically is equal to mass of fuel into calorific value of fuel. Okay. So, if we know calorific value, which is amount of heat liberated by burning 1 kg of fuel, then we can get that value, and then from that amount of fuel burnt will give us Q dot in, which is in watt. So, turbine work in watt again would be m dot g into h naught 3 minus h naught 4. So, it is m dot g into Cpg into T naught 3 minus T naught 4. So, but if we would have heat exchanger as what we would have seen, then for air there is heat exchanger and we are adding heat in the heat exchanger for air. So, as what we see here, then 3 is not the state, which is 2 is not the state which is coming to the heat combustion chamber. So, combustion chamber we will still say that state 2 is state 5 is coming and state 6 is leaving the heat exchanger, where we have 2 to 5 is heat added into the air. So, heat added in air is equal to heat loss by gas. So, we have h m dot a into h naught 5 minus h naught 2 is equal to m dot gas into h naught 6 minus h naught 4. So, we have m dot a into Cpa into T naught 5 minus T naught 2 is equal to m dot g into Cpg into T naught 6 minus rather T naught 4 minus T06. So this is what we can write down for heat exchanger based heat interaction. So thus few things to be remembered here, that we have to always use differential CPs for air and gas, differential mass flow rates for turbine and compressor, and then we have to also consider different pressure ratios, which is RP compressor and RP turbine, since there are losses in the real cycle. With this we conclude for the real cycle and its calculations. Thank you.